if you go through and look at the review questions and the practice problems, or even the extra practice problems, I want you to just take a moment and notice how many of these problems require you to do some kind of calculations. Use a formula or something like that. How many of the questions, let's just look at the review questions, how many of these, just looking at them very quickly, how many of them require you to use a formula and know the math? Right, none of them. That's typical though. Review questions tend to be concepts. They tend to be, short answer, something like that, to make sure you understand a concept. So let's go to practice problems. Practice problems are usually those things that require calculations, right? For those of you that have difficulty with math, you might be fine with review questions, but when it gets to the practice problems, you have a little bit of difficulty. So take a moment and just scan through the practice problems and tell me how many of these practice problems require you to do math? None of them. None of them require you to do math. Okay, just for giggles, let's take a look at the extra practice problems. And even if you don't, what do you suspect the number would be that require you to do math? None. Guess what? This is a module that is actually chemistry. In the sense of, hey, Mr. Baker, I can't do chemistry. I'm not good with the math. Well, guess what? There's no math in this module. This is chemistry. Chemistry concepts. So I think you're going to have an easier time getting the work done, first of all. Second of all, you're not going to have those issues. If you're still struggling with algebra, if you're still struggling with, just those basic math concepts, you really shouldn't have that difficulty in here because we're talking about chemistry concepts, not math concepts. All right. And because of the issue with second, third edition, and you all not necessarily having the guides, normally what we would do, the schedule would be on Monday, we do review, Tuesday, practice problems, maybe Wednesday, extra practice problems or review, because at that point, most of you may be struggling with the math and still need help. Even those of you that think you understand the concepts, when you ask for extra help just before the exam, it's generally on working out a formula. What steps do I do? Which order do I do them in? So I don't think this module we're going to have that same difficulty. So today is an opportunity for you to ask questions about the concepts that we've covered through this module. And we're doing it up front rather than later, because like I said, I believe if you understand the concepts, you'll have a lot less difficulty working through these problems. For those of you that turn in your homework and you go, I really don't know how I did because I'm not sure how the math is all going to work out, I think you're going to have a much better sense of how you did when you turn this in the beginning. Okay? So I'm going to take a few minutes, and maybe the best way to do this is just to kind of walk through the module again, talk about each of the key concepts, go section by section, and give you an opportunity to ask me any questions you may have remaining on the content. Or, that's probably the best way. Unless, let me be bold and let you be bold. Are there areas of this module that you know already that you're struggling with or you still don't completely understand the concept? Because I can address those first, kind of like when we do a review day, and I normally put the numbers up, which we will still do, by the way. But again, I think we'll pretty much be able to work through the entire homework assignment each day, review what was done. But if you know right now, before I mention it, because I think once we walk through it, there might be a few times I'll say something, go, oh yeah, that. I have a question on that. I want to ask another question on that. And we'll deal with those. But is there anybody right now that is willing to just admit, hey, I still struggle with something? Yes, ma'am.
The different type of bonds.
Okay, bond types. Good. So types of bonds, whether it's ionic or covalent, right? And you'll need to know what the difference between the type of bond is and when do they form. So based upon the elements that are in the molecule, what kind of a bond is being used, and knowing what kind of bond it is, describe how that bond differs from the other type. So we'll review that. Good. Anyone else? I'm just going to step back here and start the projector so I can get the periodic table on the board so we can use that as well. I'm kind of recording again just because I've got all the gear back and I've got a different camera, so I'm just trying to work out the bugs so it can start producing better content when we get back into lectures. Okay, so this is just all trial runs with the different gear. Anything else? Well, we're definitely going to get to this. So let's walk through definitions. For those of you that have third edition, I'm just flipping through. Second edition, you can join along, but I'm focusing on using third as primary. Talking about valence electrons. What does it mean for an electron to be a valence electron? What does the word valence mean? Okay, it's highest energy. Definition from the book. The valence electrons are the electrons that exist farthest from an atom's nucleus, and they are the electrons with the highest energy level number. So if I have the electron configuration of any element, what I would do first of all is look for the highest number, the highest energy level number. For example, if I have, let's say we're working with calcium 20. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. First of all, because we did this last module, you should pretty quickly be able to develop the electron configuration. Using the table, remember helium comes over here, so it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 4s2. It ends at 4s2. Now, the valence, those electrons which are the farthest from the nucleus, are going to be those that, first of all, have the highest energy level. So for the highest energy level, I'm going to look to the coefficients here in front of the different orbital indicators, right? In front of the D's, the P's, the F's, and the S's. What is the highest number that we see here in the coefficients? Well, there's 1, 2, 2, 3, 3, 4. The highest number is 4. So the highest number is 4. If, for example, we were to look at, let's say arsenic over here, 33. Well, I'm going to build on calcium. Calcium, 4s2, 3, remember I go down one energy level when I get to the D's, 3d, 10, 4p, 1, 2, 3. Okay, 4p3. My highest energy level is still the fourth energy level. Yes, I filled in the 3d. Those 3d addresses were filled after the 4s2, but it's still not the highest energy level. The highest energy level is the fourth energy level. In the fourth energy level then, if 4 is the highest number, if I just had the electron configuration and I was over here, okay, here's a 4, and here's a 4. Okay, when I count up the number of valence electrons, how many are in the farthest energy level from the nucleus, I have to add up the superscripts. So I've got 4s2, I've got 2 there, and the 4p3, 3 electrons. When I add those up, how many valence electrons are there in arsenic? 5. There are 5 electrons in the fourth energy level. 2 of them exist in the 4s orbital, and 3 of them exist in the 4p orbital, for a total of 5 valence electrons. All right? So valence, outermost, farthest from the nucleus, highest energy level in the configuration, count up all of them. 3 here, there's another fourth energy level here, and there's 2 there. And what's significant about the valence electrons? Why is it significant that we know how many valence electrons an element has? Right. Right. Basically, the chemistry, the way any element reacts with any other element, comes from this valence shell configuration. Because later on, we do the Lewis dots, and we talk about, well, how is this element going to mix with this element? Everything we've talked about regarding ionic bonds and covalent bonds, they're all based upon the valence electrons interacting with the valence electrons of another element. The completed shells, you know, those that are underneath these extras, these levels that don't contain a full octet, those are the electrons that are in play. I mean, those are the electrons that determine how that element behaves with other elements. So the valence shell electrons are the most significant portion of trying to determine how one element is going to interact with another one. You've got to understand what its valence looks like. And what the valence of one compared to the valence of another will dictate and will, you know, kind of predict the way that those two elements are going to relate to one another. What kind of bond, what proportions, 1 to 2, 2 to 3, what are the proportions going to look like? That all comes from the valence configurations. Then we related the valence configurations over to the periodic table. So as you look at the periodic table, we start to see basic trends. We said that elements that are in the same column, and this should make sense from filling up the electron configurations, but elements that are in the same column have what? How do their valence counts relate to one another? A column, column 1 elements, 1A elements. What do they have? What's similar between all of those? The properties because of what? What physically do they share in common? Louder. 1 valence electron. Column 1. This whole column here is known as column 1A. Column 1A, every element in column 1A has 1 valence electron. So we just said that the chemical properties of every element is dictated by its valence electrons and what the number is and how it relates to other elements. And we said that now that we know that every one of these has 1 valence electron. As a matter of fact, they're all in the same orbital, right? Not the same energy level, but all in the same orbital. Every one of these, more specifically, has a S1 electron in its valence shell. What about everything in column 2? How many valence shell electrons? 2. Column 2A, every one of them has 2 electrons, and more specifically, they all top off at the S2 orbital. We're going to skip over the troublesome D's right here, that whole block, and go over here to the P orbitals. This is column 3A, 4A, 5A, 6A, 7A, and 8A. And again, the number that designates every one of those columns also indicates the number of electrons in the valence orbital, or the valence shells, for each of those elements. So a column 5A element, like phosphorus, it has 5 valence electrons. Those valence electrons are 2 s orbital and 3 p orbital electrons, for a total of 5. Okay? They're in the 1 to 3rd energy level, 3s2, 3p3, for a total of 5 in the 3rd energy level. Okay? Understand that? Does that make sense? We good? I'm looking for some non-traditional bobbleheads going here now. Does that make sense? Okay. You're a traditional bobblehead. You give me feedback. I'm looking for those that often don't until after class. So if you don't get this stuff, we can spend more time on it. But so each column, the name indicates the number of valence electrons for that element. And then we have what's known as the Octet Rule. The Octet Rule, reading it from the book, says that most atoms strive to attain 8 valence electrons. Does the Octet Rule say that every element strives to have 8? No, it doesn't. It says most. You could also say virtually every element strives to have 8 valence electrons. But there's exceptions. The exceptions of hydrogen up here for helium, for example, and lithium. These guys aren't looking to have 8. Okay? They're looking to have 2. Because they're trying to go to a full S shell, because they don't even have P shells yet. They don't have enough protons to support a P level. They just want to have, you know, whether it's an S level full. So they're going to S2. Remember we did hydrogens. We said hydrogen doesn't want to have 8 electrons, and it doesn't want to lose the one to have no electrons. It actually wants to fill the s2 orbital position, so it wants to have 2 electrons. So there are a few exceptions with the very, very lowest atomic numbers. But the vast majority, every other element, wants to have 8 electrons in its valence shell, and that's why it's called the Octet Rule. Okay. So after covering octet and covering how many valence shells an element has based on where it's in the periodic table, we started to do Lewis structures, or the electron dot configurations. 2 names, same thing. I tend to try to use Lewis dot structures, but I occasionally, or Lewis structures, but I occasionally say electron dot structures or electron dot configurations. They both mean the same thing, so don't get confused by the terminology. One of them is technically what it is, the other one is named after the person, Lewis, who did the work behind establishing this as a way of us considering the valence electrons. So because it's his technique, you know, like most things in science, it gets named after that person. So we talked about drawing electron configurations, Lewis structures. I'm going to use sodium again. We'll just, with 11. 11 total electrons, but how many valence electrons does sodium have? Sodium has 1 valence electron. How do I know that? It's in column 1A. And every one in column 1A has 1 electron. More specifically, they all have a S1 electron in their valence shell. So when I draw the electron dot configuration, or Lewis structure for sodium, it has 1, and I indicate that by putting 1 dot at the 3 o'clock position. Now that's the way you would draw them initially. Recognize that whenever we start making molecules, we're going to orient the single electrons so that we can see how we can form the bonds. So there's nothing hard and fast about where the blanks have to be. But there is a standard way of drawing it initially, or considering it initially. And that's starting at the 3 o'clock position and building up from there. Let's say that we're doing the configuration for neon. Now neon is a column 8A element. What is another name for the column 8A elements? Noble gases. And they're called noble gases. They're all called noble gases, and they share a similar property in that, who do they like to react with? Nobody. They're completely satisfied. Their octet is completely full, and they want to be left alone. They tend not to react with anybody. They're also called the inert gases. So the noble gases are inert gases. They don't want to react. So if I'm drawing an electron dot configuration for a column 8 noble gas, it has 8 of them, and I know that they're all going to be full, so I'm going to draw the 2 at a time. You know, technically what I've done is 1, 2, 3, 4, 5, 6, 7, 8, but the net result is 8 valence shells electrons. And so if I have 8 valence shell electrons, and let's say a sodium goes by and it has 1, neon doesn't care. It's not looking for anything. So there's no motivation for it to react. Matter of fact, there's no motivation for the column 8A elements to react with anybody, to create any kind of relationships, because they're not looking for anything. They're completely aloof. So are there any questions on how to draw the electron dot configuration, or the Lewis structure, for any given element? We're not talking about forming bonds yet. We're just talking about drawing it for the individual atom. Okay. So what would the electron configuration for aluminum look like? Well, first we have to find aluminum, right? Aluminum on the periodic table. Aluminum is over here. So, aluminum is in which column? 3A. So it has how many valence electrons? And where do those valence electrons reside? What shells? What energy, or what orbitals? So it's S2P1 in the third energy level. 3S2, 3P1 for 3. I'm going to draw that by starting at 3 o'clock and drawing 1, 2, 3. So asked to draw the Lewis structure, or the electron dot configuration for aluminum, this is what I would expect to see as your answer. Is this still correct? Yes, it is still correct. There's still 3, each of them having those positions. But for now, as you're doing your configurations, I'd much rather you start at the 3 o'clock position and work around. Don't try to second guess it. If you were over here and say, okay, we're doing the electron configuration for chlorine. Chlorine is a 7A. I'd much rather see Cl, center, 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 you know, have it be off a little bit. Just start from the right and fill 4 and then keep going, just as per practice. When you get better at this, you might be looking at it and say, hey, I know, for example, when I do H2O, that my O is going to be my central molecule, and I'm going to have an electron pair, and the bonded hydrogens. When you get to that point where you can see that before you write it, go ahead and make your dots nice and symmetrical. For right now, though, if you were to put chlorine and go center, 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 okay, little off center, little off center, little off center, don't worry about it. Start at 3, build around until you count up the full number of valence electrons. Okay. All right. So again, no questions on how to depict the Lewis structure for any element. And we're going to be on the, just so you know, we're going to be on the A columns. We're not going to be messing with electron right now configurations for the D shells. Okay? So you'll be building those that have either in the S's or the P's is where their valence electrons are at. Right. The next section is about drawing the Lewis structures for ionic compounds. And so what we'll do is go to your review question. You know, how do we know what kind of a bond is going to form? And then we'll talk about the 2 different types of bonds and what is actually happening in each one of those. So we have 2 different types of bond. We've got ionic bonds and we have covalent bonds. Before we talk about what the 2 differences are, how do we know, given 2 different elements, how do we know the kind of bond that's going to form? Okay. For ionics, and when you say the right answer even, I pause because people may not have heard you, and I want you all to, in your own mind, not wait for the answer. I want you to come up with an answer in your own mind, and then see if you're right or wrong. That's why I'm kind of delaying a bit. So I might say, how do you know, even if we get an answer from the class, before I answer it, come up with an answer on your own. What would you say and try to beat me to giving you the real answer, okay? And then see if you're right or not. And that's one way to build confidence of, hey, you know what, I did know that. If you're waiting for me to give you the answer before you mentally come up with one, you're kind of cheating yourself out of an opportunity for review. So, how do I know what kind of bond it's going to form? Well, for an ionic bond to form, the 2 elements that I'm bonding, they have to be different kinds of elements, and that's where I get back to the jagged line and whether an element is a metal or a nonmetal. Okay? And based on that jagged line, we have said, generally speaking, and for the context of this class, that everything to the left of that jagged line is going to be a nonmetal, and everything to the left, to the right is a nonmetal, to the left is going to be considered to be a metal. With the exception of hydrogen, which we are going to, for metal-nonmetal considerations, we're going to put it over here. Hydrogen lives on this side when we're determining metal or nonmetal. Helium lives on this side when we're determining the S shell. Okay? So between helium and hydrogen, remember this periodic table is actually circular. It'd be better represented as a cylinder where they wrap around. It looks like they're far extremes. No, they're really next door neighbors. It's kind of like looking at a map. Well, a flat map, it's actually depicting a globe, right? It's round. So if you take it one longitude and say, I'm going to cut England in half, and then you lay the map flat, it looks like half of England is as far away from the other half of England as you can get. But in actuality, if you depicted it appropriately, they would be touching. The same thing's true here. This line of division right here is actually this same line over here, wrapped around. So, determining what kind of bond we have comes from, first of all, determining what kind of element we have, whether it's a metal or a nonmetal. Okay? And for the bond to be ionic, you need to have metal and a nonmetal. If you have a metal and a nonmetal, you're going to form an ionic bond. If you have a nonmetal and a nonmetal, it's going to produce a covalent bond. If you have a metal and a metal, you've discovered something, because there is no such thing. There is no potassium calcide or calciumide or whatever. They don't exist with a metal and a metal as the only two elements in a compound. If all you have are two metals, if all you have are metals, they don't form a compound, they form a mixture. So if I asked you what kind of a bond exists between sodium and calcium, you would say none. Why not? They're both metals. And since they're both metals, they don't bond together. They mix together. And that's where you might have a process where you can physically separate the mixture to get pure calcium and pure sodium. But you're not going to do a chemical reaction to separate them. You're going to do a physical separation of them, because they haven't formed a new third thing. But when I talk about, we use it all the time, but sodium chloride, okay, now I have a metal and a nonmetal. And since I have a metal and a nonmetal, I know that I'm going to have an ionic bond. If I have carbon dioxide, where I'm looking at carbon and oxygen, I have two nonmetals. And because they're both nonmetals and I have no metal involved in the molecule, it is a covalent bond. All right, so determining ionic or covalent is as simple as saying, are all the different components that make up that molecule, are they all nonmetals? Or are there metals and nonmetals mixing? And if there's metals and nonmetals mixing, it's ionic. If it's all nonmetals, it's covalent. If they're all metals, it won't react. They won't form a molecule. There's no bond that forms metal to metal. Any questions on that? So you feel comfortable that you can determine what kind of bond you have based upon given two elements, let's say. If I give you two elements, you can tell me, is it going to form an ionic or covalent bond? Okay. So then the next general question is, describe to me the difference between an ionic bond and a covalent bond by giving me what happens to form an ionic bond. If you were to nail it down to just one little principle, what differentiates an ionic bond from a covalent bond? Okay, we know that it's, ionics take a metal and a nonmetal, but at the very heart of it, why are the bonds different? What's the foundational difference between an ionic bond and a covalent bond? Exactly. For an ionic bond, it's going to be an electron transfer. For a covalent bond, it's going to be an electron sharing. For an ionic bond, one element gives up an electron, and another element receives the electron. And what happens is, since one atom has given up an electron, and the one that gives up the electron is going to be the metal, because metals would rather give up than fight to get, the one that gives up is going to be the metal, and it becomes an ion, because it's given up a negative, so now it is a plus charge. Because it lost a negative, it becomes positive. So the metals become positively charged by giving away electrons. Nonmetals become negatively charged because they're electron receivers. They take the electrons. So a nonmetal gives electrons, excuse me, a metal gives electrons, a nonmetal receives electrons. And from simple sharing, in terms of the octet rule, that satisfies it for both of them. Hey, metals, let's just give away electrons. Okay, I'm happy because somebody wants to take it. Boom, there you go. Give away the electrons. Nonmetals are being satisfied because they have gaps they want to fill. Great, here comes these electrons. I'll take it. I'll take it. I'll take it. I'll take it. And they're filling up their valence shells. But there's a consequence to that. When the metal gives up its electron and it now has a positive charge, and the nonmetal receives an electron, it takes on a negative charge, and at that moment, they have opposite charges, and opposites attract. So in terms of filling the octet rule, the transfer takes place. After the transfer takes place, now there's opposite charges, and they're attracted to one another like magnets. Boom, boom, and they come together. And so you have a positive ion and a negative ion that are attracted to one another because after they've transferred their electrons, whether they've given or received, now they have opposite charges and they're stuck together because of the electromagnetic forces that they have. If sodium gives up one electron and becomes a +1 charge, chlorine receives the electron and it becomes a chloride. Remember, the metals keep the name. The nonmetals become ides. So it becomes a sodium ion and a chloride ion. The sodium has a +1 charge. The chloride has a -1 charge. Because they have opposite charges, they're attracted. They both have the same magnitude, +1 and -1. So when they come together, the molecule that they then form with the two atoms has a net charge of 0. It's a neutral molecule because they have opposite and equal charges. So there's a plus side, a negative side. The two together neutralize each other. And so when you look at the entire molecule of sodium chloride, okay, so a sodium plus and a chloride negative, they come together and form a sodium chloride. And the overall charge of the whole molecule is 0 because the plus and the negative cancel each other out. And because they cancel each other out both in charge and in magnitude, they're both a +1 and a -1, this +1 and -1 cancel each other out. So if there are other ions in the area, if there's another a sodium +1 ion or another chloride -1 ion in the area, it's not attracted to this molecule. Why? There's no charge to it. The positives are looking for negatives and the negatives are looking for positives. Nobody wants to mess with a neutral. Okay? And so the whole molecule has a charge, a net 0 charge, but it still has a positive and negative side. Now, how would we separate an ionic molecule? How do we take these two things apart? What's the most common way we do that? Do you know? We mix it in water. When you take sodium chloride and you put it in a glass of water and you stir it up and it disappears, it dissolves. And we'll get into this when we get into solutions. Okay, so we'll do this in more detail. But when you mix up sodium chloride is an ionic molecule. When you mix it up in water, you actually make it possible for the atoms of sodium and the ions of sodium and the ions of chlorine to separate. And so when you mix it in water, it's not a matter of the molecule being so small you can't see it. You're actually breaking up the molecule and you're releasing the positives and the negative ions to be in solution. It's a little bit different than when you mix in sugar, for example, because sugar is not an ionic molecule, it's a covalent molecule. And when you dissolve a covalent molecule and you mix it in water, you're not breaking up the molecule. All you're doing is separating one molecule from another molecule. You're kind of thinning them out, but you're not breaking them down. Okay? So, since ionic molecules are formed by the differences in charges, we can begin to understand how they mix and in what proportions by looking at their valence electrons and looking at the Lewis structures for them. In this case, the ionics, we've been, again, using sodium chloride. We tend to use it all the time because it's a good example. It's a good, simple example of how this works. Let's go ahead and draw the Lewis structures. We've got a sodium, and it has a 1 valence electron. And I'm going to put chlorine next to it. And because I know I'm going to try to form a molecule here, I'm going to go ahead and put at least one empty address over towards the other element that I'm trying to match it with. I'm going to build for 7. I know there's only one opening. I'm going to leave that opening in the direction of my sodium. So there is my 1 valence for sodium. These are my 7 valence for chlorines. I know that it's going to be a covalent because it is a metal and a nonmetal. Or excuse me, it's going to be ionic because it's a metal and a nonmetal. Right? It's going to be ionic. Since it's ionic, we're not looking at sharing, we're looking at giving. So I'm going to indicate my electron from sodium to show where it came from. I'm going to change it from a dot to an X. And what happens for this molecule to form? Sodium gives up its electron to chlorine. So now I have a sodium with a +1 charge and a chlorine with a -1 charge. And so they form this molecule, sodium chloride, by that transfer of an electron to the chlorine. When the electron goes over to chlorine, it's no longer sodium's electron, it's now the chloride's electron. So an ion is an atom that has gained or lost an electron, and that gives it an electrical charge. A cation and an anion. Those definitions are in your book. The cation is the positively charged. So sodium becomes a +1. It's technically a sodium cation. And the negatively charged becomes an anion. Two different ways to designate the ions. I could say it's a sodium ion. Yes, it is. It's also a sodium cation. It's the cation. What's that mean? It became positive. If you want to think about it as cats, if you're a cat lover, then it's easy. The cats are good. The cats are positive. I like cats. Okay? I'm a dog person, so I prefer to say anion means negative. To be like the atypical means you're not typical. A means not. Not's a negative term, so I remember with A is negative. Right? But if you're a cat lover, then cat's positive, the other one must be negative. So cation and anion are the way to remember those two things. Which one is it? Is it the cat? Are you a cat lover? Cat lovers over here? Cats? Okay, so you're going to say cats are positive, so cations are positive, right? If you're not a cat person, you might just say, I hate cats, therefore it's the reverse of what I would think. But I would encourage you to say cats are positive, or the prefix A in front of something is a negation. It means it's negative of that. So since it's a anion, it's negative, so it's the negative charged ion. The positive charged cations always have the same name as the element. The negatively charged anions always have their "-ide name. We mentioned also that when we were doing the chemical formula for something, that we could determine the formula by looking at valence electrons. In the book, they talk about MgF. And if we were to go ahead and form a bond between magnesium and fluorine, there's a couple different ways we could look at that. The first way, we could go through and produce the Lewis structure for it. Magnesium has 2, right? 2 valence. Actually, to do it technically right, I'll go here and here. The fluorines, they're at column 7, so I'm going to put at least 1 negative this way. I'm going to change these to X's because it's my metal. I know I'm going to give them away, and I want to kind of keep track of them. So I'm going to try to get rid of 2. How many can fluorine take? How many can it receive? It has 7. It can only receive 1. So I can account for 1 by doing that. Oh, I have 1 more left. I need to account for it with fluorine, so let me draw another fluorine. 1, 2, 3, 4, 5, 6, 7. Empty address there. Let me take that. I've given away all my electrons. I've received all my electrons. So the ionic molecule, magnesium fluoride, because again, the cation is magnesium, the anion is fluoride. The chemical formula for magnesium fluoride is metal comes first, nonmetal comes second. I used 1 of them. For every 1 of them, I need 2 of these. So it's MgF2. Now, the shortcut way of doing that, if you remember, is to use the charges. What does it want to become? Magnesium wants to become what charge? It's in 2a. It wants to give up 2 electrons. So therefore, it wants to have a 2 positive charge. It wants to give 2 away, which makes it 2 positive. Fluorine wants to become fluoride. And to become fluoride, it has to receive how many to fill the octet? It's going to receive just 1. Since it receives just 1, now I've got the charges they want to take on. What I do is I ignore the charge signs and reverse them as subscripts. And the shortcut gives me Mg1, but we don't write the 1. The 1 is implied. F2. So you could do it by filling up the valence on the Lewis structures, and you can also do it by knowing the charge the elements want to take on and reversing them as subscripts. Okay. Questions on that? How did I do this with the charges? Okay. The other part for review, we want to make sure we get to at least a touch on, is, well, we did mention the exceptions, and if I gave you, for example, copper 4, what does the Roman numeral tell you? Pardon? Okay, so since it's a metal, over here it wants to give up, but it wants to become 4 positive. So the Roman numeral tells you the quantity of the charge. It doesn't tell you whether it wants to be positive or negative. It tells you it wants to be 4. 4 what? Well, it's a metal. It's a 4 positive. And they're all going to be in this zone when we get to the Roman numerals. So that's your cue right there. This one wants to take on a +4 charge. That's what the Roman numeral means, 4. It's going to be 1, 2, 3, or 4 in that spot. Those are the exceptions. We talked about periodic properties, the ionization energy, electronegativity, and atomic radius. Review the definitions of those, okay? But in trending, we got 2 arrows, one that increases in that direction and one that increases in that direction. The one that increases in this direction is the ionization energy and the electronegativity. As we go, so electronegativity and ionization energy increase as we go from left to right, and they increase when we go from bottom to top. Which one increases as we go from right to left or top to bottom? The radius, right? The atomic radius. So know those 2 trends. Be able to compare those 2 things. That's a really quick synopsis of about 7 pages on here. We talked about the homonuclear diatomics, those elements which prefer to form molecules with other atoms of their own type. N2, O2, F2, Cl2, Br2, I2, At2, H2. They exist as homonuclear diatomics, 2 atoms of the same bonded together. The only thing we have left to do is review covalent structures. I'll see you tomorrow. Review questions are due tomorrow.